Okay, so we are going to go ahead and get started. We might be missing our third panelist. I'm hoping that he's going to hop on, but if not, we will make do with the two wonderful speakers that we do have with us today. So welcome, everybody. Thanks for joining us on this snowy Friday. I hope you guys all have your coffee with you this morning or your beverage of choice. My name is Carly Rice. I'm the Sustainability Coordinator here on the Twin Cities campus. And we run this virtual program called Sustainability Coffee Chats. I know there's some familiar faces in here, but if this is your first event that you're joining, thanks for being here. We try to do these events roughly monthly, and we actually have 3 of them coming up in April for Earth Month. I will show a slide at the very end, just in case that is of any interest to you, to join some future events with us. But I don't want to waste too much time. I'd like to dig into our topic today, which is sustainable aviation fuels. I know this is an area that I am personally interested in and don't have a ton of knowledge on what the future of sustainable air travel is going to look like. But thankfully, we have some wonderful resources here at the U who are going to be able to speak on this a bit. These events are intended to be somewhat informal. We really want these to be discussion-based, so please ask questions. That is what we are here for. We want to just really cultivate a nice discussion here. So we have 2, potentially 3 panelists with us today. So we definitely have Dr. Shri Ramaswamy, and we definitely have Dr. William Northrop, because I've seen both of you on the call. Pat, are you here? No, Pat? Okay. Well, if he hops on, we will hear from Pat Gruber, who is the CEO and director of Gevo. But if not, we will have 2 really wonderful speakers here from our own institution. So we're just going to go ahead and get started. So Will, do you want to get started and just offer a brief introduction to yourself and your work? If you have any slides that you wanted to show, we
Yeah.
can allow you to share screen, and then we'll hop over to Dr. Ramaswamy.
Yeah, super. Yeah, thank you for the opportunity to speak with you guys today. I do have my coffee here, by the way, so I'm following the instructions. Um, my name is Will Northrop. I'm a professor of mechanical engineering here at the University of Minnesota. I've been here since 2011, primarily a combustion researcher. So I do fuels and alternative fuels and emissions from combustion, mostly from internal combustion engines and not so much from aircraft. It's kind of difficult to run those in the laboratory. But I've worked for a long time in the biofuels area, as has Dr. Ramaswamy. So I think that, I have some things to offer, I guess, with regards to SAF, and it is a hot topic these days. So I have a couple slides, Carly, so I might share those if you don't mind.
Yeah, please do.
Okay. Okay, here we go. All right, so this is based on a presentation I gave to another group some months ago, talking about renewable fuels in Minnesota. And maybe it's be of use to you guys to understand kind of what opportunities there are in Minnesota, specifically around SAF and e-fuels. I also am pretty big into renewable or green ammonia and green hydrogen. So those are maybe another topic if you want to do that sometime. We can talk about that as well. Anyways, I'm talk a little bit about fuels in general. So if you haven't been thinking much about where CO2 comes from in the different energy sectors and transportation, this is sort of a breakdown that the IEA gives. So in their efforts to meet what they call net zero by 2050, the goal is to reduce the energy consumption of different fuels and to change those over to different types of fuels. So you can see here, the red is on the left-hand plot, the red is the fossil fuels. So if you're not familiar with that means, fossil means anything like petroleum or natural gas or anything that comes from the ground. Anything that comes from the, from the dinosaurs or essentially 60 million years ago, that's the red stuff. And that's what we mostly consume today in our transportation, in the transportation sector. Now, if you consider, today we are doing some biofuels, and Minnesota is a big player in this, as I'll discuss. These are sort of what we call first generation biofuels, or ethanol and biodiesel are playing that role in the green You can see that those are projected to continue. And looking at things like electricity. So obviously in the light duty sector, we are expecting that transportation by electric vehicles is going to increase. And that's sort of the idea with regards to light duty transportation. So we're going to see by 2050 a pretty large chunk of vehicles running on electric, but there are certain sectors that can't be electrified. So, or not very easily be electrified, and aviation is one of those. And if you look and see what the expectations are here with respect to different modes on the right-hand side, you can see that aviation is expecting to consume, increasing amount of fuel. This is in exajoules. Sorry, it's in energy. This is all based on energy. And then heavy trucks are continuing to play a role here. And then, of course, light duty vehicles are expecting to emit a lot less carbon because they're going to be electrified. But of course, electric vehicles are not zero emissions vehicles. I just want to point that out. And that's something that I argue with California about all the time, is that even if it's an electric car, it's not zero emissions, because the emissions are coming from somewhere. They may not be coming out of the vehicle, but they're coming from wherever the electricity was produced. Of course, if all the electricity is produced renewably, then they are zero emission, but they don't have to be, right? So if you look at light duty vehicles, even the California Air Resources Board doesn't believe that all the vehicles will be electric in 2050. And EPA also is not planning for that kind of that penetration of electric vehicles by 2050 in the US or worldwide. So we're expecting to see, of course, the amount of energy decrease, but of course we're expecting to see, of course, that we're going to end up using these, the heavy duty trucks are going to remain about the same. Aviation actually increases a little bit. So that's the goal here, right? Is like, how do we shift the different modes that we have? All right. So if you look specifically at shipping and aviation, I do a lot of work in these alternative fuels for shipping and for rail. And if you can see, so rail and maritime shipping are on the two sets of columns on the left. So rail essentially is expected to be mostly powered by electricity by 2050. This is an international energy agency, and this is not understanding the U.S. market. The U.S. market is not going to electrify the rail system by 2050. I'd be very, very surprised if in 2050 we have an electric rail system. I think our system is going to be still powered by diesel. And that diesel could be alternative fuels like hydrogen or ammonia or ethanol or methanol. But it definitely is not going to go electric. So I don't actually believe this projection. Maybe worldwide, certainly in Europe, rail is electrified, but there is no moves to electrify rail in the US or in India, for that matter. Okay, so moving towards shipping. So shipping is another big sector that won't electrify. And I think that we're thinking about the carbon intensity of these things increasing. So if you look at the carbon intensity here, this is something I'm going to point out. So carbon intensity, maybe if you want to learn something here, carbon intensity is when it comes to fuels and transportation, is generally thought of in terms of grams of CO2 emitted per megajoule. So a megajoule is like is a unit of energy. So a megajoule is sort of every fuel contains a certain amount of energy. Like your gallon of gas has a certain amount of energy. So like, for instance, every kilogram of gasoline has 43 megajoules of energy in it. And you can convert that, if you want to convert that to electricity, you can convert that to kilowatt hours, because megajoules and kilowatt hours are both energy units. They're just different units to make things confusing. So anyways, when we talk about carbon intensity, we talk about how much CO2 is emitted per megajoule of fuel. So in maritime shipping, we're looking at, essentially this carbon intensity decreasing, which are these tan dots. And in aviation, of course, also looking at going to sustainable fuels. Now, if you think about maritime shipping, just for quickly, because I know we're supposed to talk about SAF, but thinking about maritime shipping, looking at this plot, we're not seeing very much electricity being used here, because electricity is a very, very small. So electricity is a darker blue. You don't see very much electricity being planned. You see hydrogen and ammonia being plant is the biggest fuels for shipping, and also bioenergy. And this would be methanol, probably most likely methanol. So getting in the aviation right now, all of the fuel that we burn in aircraft are, well, almost all, large majority of the fuel that we burn in aircraft is from fossil sources, meaning that it's kerosene from petroleum. And so aviation right now is going through a transition where we're looking to decrease the carbon intensity, this grams of CO2 per megajoule, down pretty drastically by using less and less fossil fuels. So to get breaking these red bars down. Okay. And then so bioenergy is expected to play a big role. Obviously some fuels from, and we'll talk a little bit about that. I think Shri has some things to say about that as well. And then synthetic fuels. Synthetic fuels are fuels that are created, or at least being thought of to be created from hydrogen and CO2 that is pulled out of the atmosphere. So those are called so-called e-fuels, which are a different process, not from biomatter. Okay, so talking about what e-fuels are, there is a plant in Chile where actually the car company Porsche is part of a project to develop fuels that come essentially from captured CO2 from the air and water that's electrolyzed to hydrogen. So take the hydrogen from water and they take the CO2 from the air and they put them together and they make hydrocarbons that are like gasoline. And you could make aircraft fuel this way too. There's no reason why you couldn't make aircraft kerosene-like fuels this way as well. This plant, the idea that it's in Chile is because they have what's called stranded wind. Stranded wind means that there's wind power. There's a lot of wind available, but as you can see, nobody's living there. So they can't transmit the power very easily to wherever the population is, but they have lots of wind. So essentially what they'll do is, the idea is that they would put these plants and make fuels, liquid fuels that could be transported out and being used for aircraft or for vehicles or whatever. The reason, of course, Porsche is interested in this is because they don't want to electrify all their sports cars. And they would rather have fuel that's sustainable that goes into their cars into the future. So this is their sort of ploy to do that. They're expecting to produce something like 145 million gallons of fuel per year by 2030 using this process. So it's a pretty exciting process, and one that I think has a lot of room to grow. Unfortunately, it's very expensive. So putting something like this together is a very, very expensive endeavor for how much benefit you get. So that's kind of something. So what do we do in Minnesota? As many of you probably know, we make biofuels in Minnesota. Much of the corn that is in Minnesota is being used to produce ethanol, and a lot of the soy is being used to produce biodiesel in Minnesota. So if you're from the rural areas, you know this already. Ethanol plants are prolific in our state. We don't have as many as Iowa, but we have quite a few ethanol plants in the state. And essentially we produce 1.4 billion gallons a year of ethanol. Now, what's interesting about it is if you've ever brewed beer or if you've ever done anything with fermentation in general, fermentation releases CO2. So these ethanol plants here, they take the corn in. The corn is then produced, is then fermented into using microorganisms into ethanol, and out comes CO2. And generally these plants release the CO2 directly into the air. It's a pure stream of CO2, which is interesting because it's not diluted with anything else. It's just pure CO2 coming out the stack. And it generates a lot of CO2. 4 billion kilograms of pure CO2 is generated. If you convert it, and I just did a quick calculation, and this is the same if you plug in SAF here into this thing, pretty much the same, because SAF and gasoline are in some sense similar in terms of overall density. So if you have 4 billion kilograms of pure CO2, if you use that CO2 to make SAF, you could make 616 million gallons of e-gasoline per year. That's cool, except that you need a lot of hydrogen to do that. And so a lot of wind turbines would need to be used in order to convert all that CO2. But that's a real possibility and something that my research group is actually looking at, using the fermentation CO2 to make ethanol plants more renewable. Okay. So anyways, it gives you a sense, what's going on. Of course, Minnesota does not want to lose its ethanol industry. It prefers that it keeps that industry around and converts it to something. And if our colleague from Gevo is here, I'm sure he has a lot to say about that. I don't know if he's joined us yet. So anyway, so if we look at what Minnesota is doing, we have Delta Airlines here. Delta and others in the government have launched a SAF hub, or Sustainable Aircraft Fuel Hub coalition. The university is involved in this in some ways, and professors individually are involved in this. So looking at first moving from an ethanol to SAF idea, so taking the ethanol that we're producing and making SAF out of it, and then waste biomass, and eventually some of these e-fuels or hydrogen-based fuels for renewable resources in Minnesota, such like wind or other things like that. So this is a big push for Minnesota. A lot of other states are also doing this, and essentially looking to capitalize on this new market that could be coming for aircraft. Let's see if I can keep going here. Anyways, this is my last slide. So SAF, and this is, remember, I'm going back to carbon intensity again. So this is grams of CO2 per megajoule. All right, so and this is a big point of discussion in the community, essentially, and something that I don't even really have a good handle on at this point. What counts as SAF is the question. So if you think about what the community or organizations have set what they think fossil jet fuel's carbon intensity is, and it ranges between about 84 and 94 grams of CO2 equivalent per megajoule of fuel. And so that's the baseline. So that's what we're burning now. So the question is, how far do you need to go down in order to quantify it as sustainable? And sometimes, there's some thoughts that you can even make this carbon intensity be a negative thing. If you just look at, this is from a Department of Energy report online. Essentially, they have these different processes for making SAF, and there's different ideas using agricultural wastes, which I think Professor Ramaswamy is involved in, agricultural residues, which is also considered like agricultural wastes. But if you look at the ethanol plan, and if we consider what they call indirect land use change, which is a subject about how you change the use of land to grow corn or other crops. Essentially, what it's looking like is that ethanol plants, as they are making SAF, is not really enough to create a quote unquote renewable fuel. It's renewable to some extent. It's better than fossil fuel, but it doesn't get you to some of the goals. And in Europe, I think one of the goals is a 65% reduction compared to fossil jet fuel. And if you think about that, this bar right here, essentially we need to get down to that bar, and bringing the ethanol to jet or ethanol to SAF down about half of what it is right now is going to be very challenging. So looking at other processes is a good idea. So essentially the plan here is to figure out how much CO2 you release from each of these different processes and how much they cost, and compare those things. And of course, it has to be economically viable as well. And so this is the trade-off that people are making. The ethanol industry, as I know quite well, is very interested in getting their numbers down so that they can meet these requirements. So that's the big deal right now in Minnesota. So yeah, so that's all the slides I had. So Carly, so hopefully that's enough.
Well, thank you so much. And we will definitely get to some questions. I just want to make sure that all three of our speakers have time to give some introductions. Pat, are you ready and able to chat with us?
I could chat with you, so apologize.
Amazing.
I'm doing this with my car. I got hung up on airplanes and stuff, and
No
so
worries.
sorry for that. Yeah. So, how much time do you want me to talk here? What do you want me to do? Give me the rundown real quick.
Yeah, for sure.
missed-
So we have about 35 more minutes. So I
Okay.
would say 5 to 10.
All right, I'll probably take 10 because I was just looking at
10
the
is
data
great.
that Will just went through, and there's obviously we have a different point of view on many things. A lot we agree on though. So Gevo is a company that is committed to doing carbohydrates to alcohols to olefins into hydrocarbons. Olefins are the building block of the petrochemical industry. So We're in the midst of commercialization. And so we have all real data. So all the stuff that I'm going to talk about is based upon real data. And this also includes HEPA, which is the oil seeds approach to make jet fuel. We work with that. We've worked with alcohol to jet of all different types, methanol, ethanol, butanol. We've worked with Fischer-Tropsch and powered liquids. So we've worked in all of those things and have definite opinions about what works and what they cost. I just spent about $3 million with McKinsey doing the deep dives on all the economics and matching it up with our friends and competitors to figure this out. So when I'm talking about this stuff, it's from a real live, I have engineering data point of view of what it is. And then likewise, we've published our stuff and worked with Argonne National Labs and the GREET models and doing field measurements. So first I'll start off with the state of the marketplace. Nobody wants to pay for carbon. Nobody. This is the reality. Airlines can't afford it. It's their fuel price eats up their cost of production, or their COGS in a business term that's like 70%. They can't tolerate much of an increase at all. This is a fundamental point. So who is it that's going to step up and pay for this? Well, the good news is that there's market subsidies available here in the States, and there's market mandates in Europe that might get things started. The way that this works is that these jet fuels, by the way, are all proven so that they work and fly. That's no question. So they have a value of Jet A. They're just Jet A. Okay. So that's worth some money. And then you can get what's called a RIN. That's from the RFS. That's worth a couple bucks. You can get a state level subsidy of another $1.50 or something in some states. Minnesota's working on it. And then there's in the IRA bill, there's a pay for performance provision called 45Z in the IRA bill, which if you can show that you get a 50% reduction, and then you get 3 cents per CI point reduction for improvements down to 0. Now, CI score is the shorthand way of talking about what Will just showed about his grams per megajoules. So we talk about CI score. So a typical jet fuel might be a 90 CI score. So you got to get to a 50% reduction. So 45 or 50 CI score from 90, and then you get points and rewards. Maybe there looks like there's enough money here to get something done. So we have been looking at the scalability economics overall. Now the marketplace is sorting out and thinking about it this way. It's very different than what people would think about. There's a gallon, and then the carbon abatement attached to the gallon, and they can be together or detached. In other words, it's just jet fuel. It's a commodity drop-in. It goes into the pipelines, goes in the wings of the airplane, and off it goes. The carbon abatement is that carbon reduction that we're talking about. The key here is you have to verify it the whole way through the system. I'll come back to that. But you've got to document it and verify it and drive it down. Now, in terms of, we've been doing a lot on ethanol to jet. We have a large project that we're developing in Lake Preston, South Dakota, and actually would pencil out to be about a minus 30 CI score all in. And so that's negative across the way using ethanol. It starts with pretty much what Will said. If I did a typical ethanol plant and I just said, it just did grid electricity, grid energy, grid everything, and just normal corn and all the rest, it might be, up in the 70 something to 90. We would pencil it in at about 90 if it was doing ethanol first and then making the chemistry into alcohol into jet fuel. The way you decarbonize it is you replace the electricity. That's worth 18 CI points. Getting rid of the natural gas and integration with thermal energy, and this is something we patented, is how do you do that? That gets rid of another 40 points about. The hydrogen's 5 points. So already that's mostly reduced. And then with carbon sequestration, which is the most valuable thing you can do with CO2 that's coming off of a fermentation plant, you put it in the ground. That's the most valuable thing you can do with it currently. And the market may change someday, but that gets you another 32 CI points. And then with agricultural, both agriculture practices about precision agriculture, climate smart agriculture, what's done on the surface, like for instance, reduced amounts of fertilizer, optimization of fertilizer application of herbicides, pesticides, how many times you go in the field. And then also with the tillage practices of strip till, no till, where you're building up soil carbon. Those things all matter. That can be actually a very huge number. We don't count it much. We just get down to, that's how you get down to our minus 30. For commercial purposes, we target a 25 CI score for contracts, but in fact, the plant has the capability to go very negative. What's interesting is that we've been doing field work with farms for the last several years. And we're doing a technique that we call verity tracking. And it is a blockchain system where you track stuff on the farms, all the stuff that gets applied, and document the heck out of it, measure all the stuff, measure the soil carbon, and then attach it to the corn. The corn goes in the plant. You take that, measure all, when you process it, you measure all the energy, and you can document all of this. So there's another theory that we have, is that in the end, we got to have field specific measurements, field specific measurements, not regions, not generalizations, real specific information, document that we have the capability from a technology standpoint to do that. So it's crucially important, because in the end, it's taxpayers and consumers are footing the bill for that carbon value. Got to prove it to them that they got something for their money. That's reality. And ideally, we put it down to the seat of an airplane. We're already working on that with airlines. So what's interesting about this then is we have the methods where we can track carbon. Good. We see the methodologies of how you can drive to net zero. If you want to, you got to have renewable energy as the primary thing. Cool. That all works. And then the question is, which technologies make sense and where? It is not one size fits all around the world. It'll depend. In a place where you have stranded wind, or you have stranded whatever, making liquids for it might be a practical thing to do. The way that the costs stack up are these. So the question is, how do you make something that's cost competitive? The alcohol to jet process in an integrated plant where you've integrated the ethanol into the jet fuel, the cash cost of production is about the same as petrojet cost, which is pretty damn amazing when you consider what we're talking about here. That means if the plant was paid off, guess what? You can have a net zero product, except for it costs the same. Well, but we have to pay off new capital. That's a significant chunk of money to pay off. Well, that's what that carbon value from the marketplace does. The lowest cost method of making a SAF is by an integrated ATJ plant, including the cash cost plus the capital returns. Okay. And that total cost without subsidy is probably around $750 to $850. That's the same as HEFA. Okay. Now, the difference between HEFA is the process of taking and making waste fats and oils and or soybean oil or something into jet fuel. The difference here is that with HEFA, the cash cost is much higher. It's about 2x of what ethanol to jet is, but the capital cost is lower. So when investors look at it, you got to look at how it works over the long run with paid off plants. ATJ wins. Powered liquids is costs about $14, $15 on a good day to make a gallon of fuel. It's about so it's very expensive. The reason for that is it takes 3 pounds of hydrogen per gallon of jet fuel. A photosynthetic route like HEFA or ATJ takes 0.1 pounds of hydrogen per gallon of jet fuel. So it's that real practical thing. If you did a plant that of 65 million gallons using powered liquids in the US, it would take 20% of the US demand of green hydrogen in year 2025. So there's work to be done on this. And it is a thing that I think is everybody who's in the space knows this. You can't get there from here on powered liquids. It only work in places like Iceland has a great project. They're trying to do energy security for Iceland. Awesome. They don't do Wall Street calculations. They're doing energy security calculations. In Chile, it's a different calculation. Same thing on the east coast of Canada, there's going to be one. Same reason. They got stranded wind. They're looking to create jobs, businesses in an area that's underdeveloped. Saudi Arabia will be the same thing. So it isn't to say one or the other, but it's not a Wall Street calculation to gain investment, which means then it's something that can be done, but nobody will pay for it. Think about this. The carbon abatement cost is what the market is interested in. Integrated alcohol to jet, the carbon abatement cost is about $450 a ton. Okay. With the subsidies that exist, that means we can deliver price parity jet fuel to airlines and still make money to get returns for investment. Okay. The HEFA carbon abatement cost, the total carbon abatement all in, is about $600 to $850 a ton. That's what it costs. Powered liquids is $2,000 a ton. Fisher Trupp's is 10 to 15. A non-integrated ATJ plant, where you have an ethanol plant disaggregated from the ATJ plant, is about the same as a HEFA plant. So what this means is, if you think that each $100 per ton of carbon abatement translates to $1 per gallon about of a jet fuel cost. So what that means then, if we have a $450 a ton carbon abatement cost, that means we got to cover $4.50 through government value or somebody's value in the marketplace for that carbon to get it to net zero. If it's $2,000 a ton like Power Liquids, that's $20 a gallon premium has to be covered. Okay. Fisher Trups would take, about, it's about $10 to $15. The energy intensity is very high for Fisher Trups. And so it is this very practical matter of what happens where and how. The fundamental issue is not about the feedstock, oddly enough. It's about energy itself. That's electricity, natural gas, infrastructure. The climate smart ag program that the USDA has put on, with several $billion being invested, is to start really documenting the good practices and develop the big database. And of course, with our Verity tracking, we've been doing that. We're in the midst of financing a plant, like I said, in Lake Preston, South Dakota. The technologies are known for all these things, and even can be done. Even Power Liquids is like, that's a known technology too. We can do that anytime. We can even do it. And so same thing with all the HEFAs and all the rest. Those are not where the challenge is. Fisher Trups is different. Fisher Trups is more complicated because of the mixtures. But the rest, all known stuff. This isn't a technology question. This isn't. This is about financing and deployment and economics and building a marketplace. And then asking, who is going to pay for this? And here's a real fine point on it, if there's any business majors in here, is that the question comes down to something real specific is what we're working on. We need to put debt on this project. Debt guys go, hey, wait a second, what's the carbon value 10 years from now? What's it 15 years from now? What's it 20 years from now? You're asking for a 20-year financing. We got to know what the carbon value is. Well, that's an unknowable. That actually is unknowable. Government policies are subject to change. And so this is actually the real live problem for building out an industry like this. It isn't technology. It isn't about the feedstocks. It's none of that. This is down to one question. It's true, not just for us. This is also for the broader HEFA and the rest. And I think that we'll see PTL happen in certain places because it makes sense for other strategic reasons. And Fisher Trups will work in certain places because where they have special situations as well. But that's the state of play in the overall game. And we do have, if you guys are interested in it, we have this whole McKinsey study. I'll just send it to you. And then you can see what $3 million buys you in terms of analysis on everything. And ours is based on real data, not hypothetical. So it's one of these things where it's fascinating to look at and see, but we'll just share it and see, because it's the only way. There's so much BS in the space. It's mind numbing. I was in Washington, D.C. last week doing talks, and I was at World Bank, and I was at, this big agricultural conference, and I was down in Sarah Week, which is all the oil, gas and oil companies this week. And it's mind numbing. People talk about it as if it's difficult to do. This is not actually technically hard to do. It's not. That's wrong paradigm. Anybody got economics that work? What's the carbon value? Does anybody care really? How do we know? Who's going to pay for it? How do you get the returns? That's reality. So that's our kind of in the trenches opinion of the state of the play. And the good news is this: it's economical. It can be economical. It can work. It can be financed. We got to finish working through it. The airlines, and Delta's been a good partner. The airlines are, they know that they're under constraint, and they're looking for help as to how do you subsidize carbon value. And it's pretty interesting. I can say this too: the paradigms that we've seen in the giant public policy globally and in the US, these biases that people have about row crops are profound. It's simply that row crops are always bad under all circumstances. There's an underlying bias for that. In fact, there's a bias even stronger. It says there should be no farming, no row cropping, no agriculture. That's actually a belief that we fight every day, and we do it with data, and we win with data. And so there's this, for everybody involved in a school like Minnesota, there's a change that's occurred. no longer in the as you guys grow up, in the future world is going to be looking at data that cuts across agriculture, all the things related to it, the accounting for everything that happens, and actually, I mean, measuring, accounting, the systems to account, the AI that goes with it, the data collection, and all the rest. Also, the business. So it's a big business system approach that has to be done to get this right. Otherwise, simply the wrong analyses get done. Okay.
Thank you, Pat. We really appreciate that perspective. Like I said, we have a third speaker, so I would love to introduce Dr. Ramaswamy to introduce himself and his work, and then we should have a few minutes at the end for some questions.
Thank you very much. Can you see my screen and hear me? All right, great. See whether I can do a slideshow. All right, good. Works. Can you see it? All right, thank you very much again, Pat. It's a pleasure to see you and follow you on this panel. And thanks, Will. That was a good overview of the carbon implications of SAF. So what I'm going to provide a perspective on is actually what about the sustainability of biofuels and how can we improve it? I think Pat talks about the carbon credit that one can have in the future, but actually today's biofuels manufacturing, in the near future, can we actually try to improve the carbon footprint of biofuels? So that's what I'm going to talk about, which has an implication in SAF, because as they were talking about, ethanol produced in Minnesota can be used in sustainable aviation fuels. So what we are trying to do very briefly is take one part of this process and trying to improve it, intensify it, so that you can actually reduce the carbon footprint of existing biofuels manufacturing and contribute to the future SAF. So our main objective in this work, and I think the goal of the SAF that you saw here is actually the federal government has, I guess, stated that we would like to reduce the carbon footprint by 50% reduction in life cycle greenhouse gases, and compared to conventional petroleum-based jet fuel by 2030, and produce 35 billion gallons, by 2050. So this is kind of the goal set by the U.S. government. So this is what we are working towards. So the work that we are specifically doing actually has to do with improving the sustainability, and more specifically, reducing energy consumption, reducing water consumption, and reducing the carbon footprint, okay, which will be reducing the grams of CO2 per megajoules of energy. And also, in addition to using corn-based ethanol, can we use low-impact feedstocks? And that would contribute to the carbon footprint. And of course, the economics has to make sense, in all of these cases. Okay. All right, so just as a background, those of you who are not familiar with the corn-based processes in Minnesota, very simply, we take the corn that is grown in Minnesota and use two different processes called the dry milling and wet milling to produce the ethanol that you see on the right-hand side. So ethanol is one product, but in addition to ethanol, you also can produce animal feed, and you can see the gluten and also the DDGS. These are the byproducts. So primarily, ethanol and corn in Minnesota can be used as animal feed directly, but also is used as for making ethanol. And I think Will talked about producing 1.4 billion gallons of ethanol in Minnesota. I think that's about 10% of the national total, if I'm correct. Okay, so what we're trying to do is to take this process of making ethanol, and the red circles here point out the place where we consume a lot of energy. So today's processes, by distilling the beer, you consume a lot of energy, and that is coming from natural gas, which is essentially a fossil fuel, right, primarily. So now if you look at the process that you can improve is substitute some of the distillation with membrane, which actually requires less energy. So you want to substitute a fossil-based energy process with a low carbon or a renewable energy-based process, like electrifying some parts of the process. So this will essentially reduce the carbon footprint. So this is suitable for ethanol. It is also suitable for isobutanol, one of the products that is made by Gevo. So I think we were talking about this carbon footprint and the SAF's greenhouse gas emissions. So this is actually a work that is done by Oregon National Lab that Pat was referring to. Pat, it looks like they actually took your base case and various methods by which Gevo is planning to reduce the carbon footprint. So the two things that I would like to point out here is if you look at the leftmost column, so that is your petroleum-based jet fuel that is currently used. So about 84.5 grams of CO2 emitted per megajoules of jet fuel. I think Pat and Will were talking about 80 to 90. So this is the 84.5. And if you compare the life cycle analysis based methodology to compute the greenhouse gas emissions as stated by the Oregon National Lab people, you can see that the corn-based ethanol through the wet milling process and then ethanol converted to jet fuel, as Pat was talking about, is about 70.4. Okay, so this is about 16.7% less greenhouse gas emissions compared to today's petroleum-based fuel. So it is good, but it gives us an opportunity to further improve. And you see the right-hand side bars, these are essentially various methodologies which Gevo is in place in their plans to implement over the next several years to essentially reach net zero, greenhouse gas emissions. So basically, instead of 84.5 by the current jet fuel, you essentially want to go to 0 grams of carbon dioxide. Okay, so, and of course, they have various ideas on how to approach it. And what we talked about here, this membrane solvent extraction, is essentially making this 70.4 number lower, okay, compared to what it is today. So that's where we are working on to reduce this carbon footprint, right here. And these are normally measured and analyzed doing what is called LCA, or the life cycle assessment. And the ATJ that Pat was talking about actually is alcohol to jet fuel. So we're making alcohol from corn, and then from that alcohol down to jet fuel. So one other point that I would like to bring here is if you look at what about the sustainability of biofuels in general? Are they really very sustainable compared to gasoline that we use, right? And there has been work on this for more than 20 years and a lot of discussion and debate. So the point I would like to take here, for you to take here, is if you look at the gasoline from petroleum, the bar here shows you it's about 70, 80, 85 grams of carbon dioxide per megajoules of fuel from petroleum-based gasoline, which is similar to the jet fuel that we saw in the previous slide. And this bar shows you the corn ethanol, which is again through the wet milling process, etc. And it's about 24% reduction in GHG compared to petroleum-based gasoline. So if instead of making corn-based ethanol, you actually use lignocellulose-based ethanol or waste biomass, etc., you can actually get down to close to zero, okay, on cellulosic ethanol. So now if you take this and convert this into jet fuel, you would have a significant impact on the overall carbon footprint of the jet fuel that we can make. So the bottom line in this is that the current technology to make alcohol to jet fuel, which is what Gevo has indicated, and also it's used in that paper, is a potentially viable solution to producing SAF. And of course, the economics is something that Pat alluded to in terms of the cost per gallon. And I think this provides a good opportunity as a first step for making sugar to alcohol and then to go from alcohol to SAF. And also, if we can continue to advance the technology for making second generation or a third generation biofuel, I believe this will actually spur new growth and advancement in the industry. We can actually use waste residues. And this would actually make the carbon footprint of the SAF produced in the future even better. I think I'll stop there and open for any questions.
Wonderful. Thank you, Dr. Ramaswamy. Big thank you to all three of our speakers. We do have about 10 minutes left, so I would love to open it up to any questions. Feel free to just unmute yourself. We can do this fairly casually. So what questions do folks have for our speakers?
I just want to add something about what Shri just said. Here's something else: as you guys are being brilliant in figuring out things, here's something really important. The sensitivity of agriculture, this is a cost sensitivity, cost of production sensitivity is what I'm going to speak to. Think of this: every 1 cent change, 1 cent change per pound of a carbohydrate cost results in a 27 cents raw material contribution cost changed to the jet fuel. It's incredibly sensitive. Okay. Now think about the chemistry. You're capturing, you got the CH2O is the generic formula of a carbohydrate. Well, you're getting rid of waters off there and combining and keeping the electrons in place to make the jet fuel. That's actually what occurs chemically in the process. So it's a shrink. It's a shrink. A mass shrink is why that occurs. That means then we need more. You can't tolerate these cost increases. A cost of a sugar from starch in the Midwest is about 7 to 10 cents. Okay. Cellulosics currently are 20 to 25 cents. That's several dollars per gallon more cost. That's a problem. And then the other one that I would add in the cellulosics that has to be solved is not all things are created equal. It is not, some cellulosic processes are low carbon footprint, others are not. And so that's also critical. So it's those things that matter as well.
Thank you. I have a question in the chat from Eric. Are there any studies on consumer confidence and trust in the alternative jet fuels, or positive statements, willingness for airlines to use them on extra, he means an extra cost?
So one, we've been flying since 2016. It's been used all over the world. We flew like 1 million kilometers in Australia with Virgin. It's been used everywhere. So they're proven. You don't get to, we had the ASTM certifications. So when I see these are exact replacements, I'm not joking. They're drop-ins. And so it has to be that way because no one's changing any energy. I was on the first flight from doing wood. We made wood jet fuel, drop-in jet fuel, but from wood sugars, like Shri was just talking about. We did that in, I don't know, within 5 years ago, and I was on board and the people were, it was funny. It was Alaska Airlines and people were at first going, really? And then the guy who's doing it is there and made them all feel better. But then they're like, well, it's just the same. So it's invisible. And legally, we take, the way it works is that we make the SAF certified according to spec, blend it with Petrojet, Jet A, certified, look at it again, measure it, make sure it's in spec. Then it all is Jet A. It isn't SAF at that point. It's Jet A. And so it is the same. And so that's what's interesting about it. Another question that's related that comes up is that could you ever do 100% replacement? Yeah, you can. Virgin just flew a plane from London to New York on 100% renewable jet fuel. And it was done by a couple companies getting together and supplying stuff to make it happen. So that part is straightforward. And then as far as I can tell you, no airline is willing to pay more. None. Zero. And so that is the issue, and it's a financial issue. They don't even have strong enough, in general, don't have strong enough balance sheets to back a take or pay contract that take or pay contract that debt lenders would like. That's a challenge in the industry. So a company like World Energy has solved that by taking and detaching the carbon abatement value and selling it to customers who are beyond the airlines. They're customers of airlines. So that's also a possibility to deal with this.
Thanks, Pat. I see Lola has their hand up.
Hi, thank you all for speaking today. I have a question specifically for Pat. I'm kind of wondering where the relationship or partnership with Delta started with Gevo, and if you could just speak a little bit more on that, like when did it start, who reached out to who, that sort of thing.
Well, for all the airlines, it's us reaching out to them. We had to teach people about alcohol to jet because people generally have the analysis wrong. They don't know because they're just looking at reading, popular press, or I don't know. They didn't have facts. We're loaded with facts and data. We've been doing this since 2007. And so we get tons of information. So sitting down with them. So we got to know them. One of the things that we've done is we have a plant down in Laverne, Minnesota that makes ethanol, makes butanol. And then we also work with farmers in that region who are very, very good farmers using modern agricultural practices. We've done a program with Delta where we brought 150 of their customers down to our plant at Laverne to show them how this would work, what it means. They're shocked when they find out you get 3 tons of animal feed per ton of jet fuel produced, because it's like, what? It's not food versus fuel. Oh yeah. And most people don't even know that corn that we're using is field corn. Only 1% of the corn of the US is for human corn, the corn cob or popcorn and all that stuff. The rest of it isn't that kind at all yet. So most people don't know that. So it's a practical thing. 150 customers of theirs, and then we take them out to the farm and show them what modern agriculture actually looks like. And I can tell you, to a person, they're stunned because it's not what the enviros say. It's completely different because they're using modern agriculture, precision agriculture, cover crops, and they're doing it to they plant these giant radishes, and the giant radishes break up the soil, so it makes it easier to do the strip till. You guys are familiar with strip till plowing? They leave the root systems intact, and only put the seeds in a narrow strip, and then they move it from year to year to build up the root systems. But they plant these cover crops, and it allows more water penetration. You know what that means? It's the fields are more moist, and so then during a dry spell, the corn grows better and they get a better yield. So you actually are seeing yields improve while they're doing these sustainable agricultural practices or regenerative agricultural practices. So we show people what that looks like, or they see John Deere's tractor that does and spraying equipment that has all these cameras and AI on it. It recognizes the darn weed as it goes by with a camera and then shoots the right herbicide on that weed specifically. So it doesn't do broadcast spraying. It does specific. That's what the future world looks like. And all that data we capture. We can capture that and report it. And that's how we have to fight back against enviros, is collect the darn data. It also helps the farmers then say, well, I did this on this field. Here's the data. It's like any process improvement. I got the data, measure it, and ask how you can improve it and compare it to something that didn't work right. And so it's going to turn into more of a processing thing around agriculture than what people think. And of course, we love cover crops. We love this program that Minnesota has on cover crops. Bring it. Let's go. Guys like me, you'll go, no problem. I can process that stuff and make it into something valuable for hydrocarbon space. That's easy. I got all the techniques to do that. That's not hard. So remember, my paradigm is this is not a technology issue at all. This is a systems issue. And it's about a value in the marketplace issue is what this is.
Thanks, Pat. I know we're just about out of time. I do have one more question in the chat that I would love to get to. Cassidy says, regarding the CO2 byproduct of creating ethanol and other biofuels, what is the status of point source carbon capture and storage or direct air capture technologies at biofuel plants? Says companies like CarbFix and Heirloom are making great progress with capturing CO2 and sequestering it in basalt or using it in industries such as cement. That might be a big question for 30 seconds here.
Yeah, I can tell you about that. So all the ways of doing carbon capture are pretty much straightforward. We have a concentrated CO2 stream. So we've looked at all those things. There is no question we can make methanol quite easily. I have all the raw materials to do it. It doesn't make any economic sense to do it at all. I can tell you that. It's more valuable to put it into the hole in the ground. It's more valuable given the way the economics work. The technologies to make it into stuff and remember, think this way. We're trying to abate carbon. That's what the marketplace is interested in, abating carbon that goes to the atmosphere. So if I take it, make it into another fuel and then burn it, you didn't really abate that carbon value. Someone's going to have to eat that and take a hit on their CI scores, and you're getting paid for carbon abatement. That's the issue. Now, if you make it into a durable good like cement, awesome, great. That is possible to do, and people are doing that. We'll see more of that in the future, or we'll see CO2 put into durable goods. That's also possible to do. That because the chemical market is so darn small compared to the fuel market, those will be follow-on applications. It'll be follow-ons. So we have the full ability to take CO2, apply it. We got renewable hydrogen at a plant like ours, and we have it built, and we can make olefins, and olefins are the things that make plastics. So that technology, we'll deploy it when we figure out the economic case, but it's a follow-on. It won't drive the development. It's too small.
Wonderful. Thank you. Honestly, a huge thank you to 3 of our panelists. Will unfortunately had to hop off to another engagement, but thank you all so much for joining. I wanted to just put up this screen super quickly. We do have a series of 3 coffee chats on climate resilience coming up for Earth Month. Stay tuned to our website and our social media if that is an area of interest for you. And thank you all so much. Again, Dr. Ramaswamy, Pat, and Dr. Northrop, who had to hop off. Thank you so much for taking the time. We really appreciate it. So hopefully we will see you all on a future coffee chat.
Thank you.
Thank
Cool.
you.
Thanks.
Bye.